Good afternoon, everybody. Welcome to this week's Green Bank Observatory Community Zoom. Some updates on what's happening at the observatory. I have some good news. I'm going to share my screen briefly so that you can you see my screen? Yep. So
yes,
as you know, there was we had a damaged wheel on the telescope, and the good news is that yesterday the wheel came off. Oops. If you can see, that is the old wheel. The assembly is turned over, and the assembly was taken apart yesterday. Here's the new wheel that is ready to go. It was kind of interesting. We jacked up the whole telescope is sitting on 2 jacks and bearing the weight of it's about 1 million pounds, I guess. So that's kind of cool. And then let's see if I can find this one. There you go. Here is the old wheel and the assembly. You can see the assembly that houses the wheel has been taken apart. What's going to happen? I think this has already happened. The old wheel needs to be removed and the new wheel put into the assembly. The assembly reassembled around it, tipped over, and slid back into the proper slot. So that should all happen today and tomorrow. So that's very good news. The contractor who's working on the foundation and the grout will come in next week. They're starting Monday, and we should take care of all the grout work next week. So fingers crossed, within 2 weeks we will be up again and operating. The first order of business is to inspect all the wheels carefully. We weren't able to inspect all the other wheels to see if there's any signs of damage or fatigue. So that will take place next week while the grout work is happening, and next community Zoom I'll have an update for you. But if all goes well, we should be up in the air very soon. All right. So the other thing I wanted to mention to you that there is a new RFI GUI available to Green Bank observers. If you have an account on the Green Bank network, rfi.gb.nrio.edu. rfi.gb.nrio.edu. That will take you to a web interface where you can look at RFI around the frequency of interest, around as a historical record. Has the RFI changed over time? There's a very nice display there. So if you're interested in using that for your next observing proposal, or just curious about RFI here, congratulations to our software team. Casey has done the heavy lifting there, and she's done a great job. So that'll be a nice tool for our community. All right, that's all I have, and I'll hand it over to Jay Lockman, who will introduce today's speaker.
Thanks very much, Jim. Today's speaker is Antoine Marchal from the Australian National University, and I'd like to say that we appreciate very much him getting up before dawn to do this from across the Pacific. And he'll be speaking about mapping the thermal condensation of diffuse H1 in the North Celestial Pole loop with the GBT. Let me remind everyone to submit questions through the Q&A button that is in the lower part of your screen, and also that this seminar is being recorded and will be available for viewing probably by tomorrow on our website. But for now, take it away, Antoine.
Thanks, Jay. I'm going to share my screen. Hi, everybody. Well, that's my calendar. Can you see this?
Yes.
All right, great. So good morning, good afternoon. My name is Antoine, and I'm going to be talking today about the origin of the North Celestial Pole loop and how we can map its multi-phase structure with GBT data. This work has been done with Peter Martin and our 2 students, Mukesh Tank and Luca Bucheva, when I was a fellow at CETA. So what is the NCPL? The NCPL, oh, sorry, I have to move something on my screen. There is a window in the middle of my slides. Sorry about that. All right, it's good. So what is the NCPL? It's hard to miss the NCPL when you look at full sky map. Planck, for example, it's one of the most prominent structure of the high latitude sky. It has a very distinct loop geometry, and we think it's more like a large scale filament rather than an H1 shell. For the reason that when you go through the PPV cube of H1 data, for example, you never really see H1 at the center of the loop, even at different velocities, which is usually how we detect shells. There is formation of molecules within the loop, within individual dusty H1 clouds. Some of them has even turned molecular. Some of them are part of the MBM Clouds CO catalog that I'm sure you're familiar with. That was mapped in the late 80s. And the three main regions along the NCPL are Ursa Major, the Spider, and Polaris. Those regions have been extensively studied. It would be hard to cite all those works, but I would like to cite some of them and list some key properties that are going to help us understand the origin of the loop. Among these properties, the magnetic field is very important. It's been shown that the magnetic field is higher than in the local ISM. There's an enhancement of the magnetic field strength along the loop. And there's also some sign of coupling between the magnetic field lines and the gas. So all this together seems to indicate that there is some compression, there is some dynamical process that might be at the origin of the formation of the loop. And this idea was really bolstered in the 90s by the fact that we also observe an enhancement of soft X-ray at the center of the region. That seems to indicate that there is really hot gas, a hot cavity that might also be elongated along the line side, and through pressure gradients might expand laterally. There is no OB stars, and that suggests a more distributed source of energy as opposed to a point-like source or multiple supernova like the per tau shell, for example. Last but not least, H1 data show a very distinct velocity gradient from the north western part of the loop to the south eastern part of the loop. And that was used in the 90s, 91, by Meyerdierks to fit a model for the cavity that is an expanding cylinder. So today I would like to show you how we can sort of confirm and revisit this picture and what we can learn about the multiphase structure of this H1 gas. So we're gonna try to turn this early picture that was honestly quite accurate and amazing to read into something that fits our current knowledge of the structure of the gas in the solar neighborhood. So we're going to be using high-resolution GBT data that were published as part of the GHIGLS survey by Peter Martin, 2015. And also we're going to be using 3D dust extinction data thanks to the Gaia Observatory. So the story starts in the H1 phase. This is a work that was led by our student, Mukesh Tank, who was a grad student at that time, and I would like to highlight also the contribution of Luca Vugeva. The map you see here is a total integrated column density map of the H1 in the region of the NCPL. Inside the dashed black contour, you can see GBT data, and outside some data from the EBIS survey. They're almost at the same resolution, but the GBT data has slightly higher spatial resolution. So to understand the multiphase structure of the NCPL, we try to decompose it into different phases inside the region that you can see with the white square here. That there is cold gas in the NCPL is not something new, and we also see the formation of molecules, as I said. It's been also shown that the temperature of the cold H1 is around 60, 70 K. There is a high fraction of CNM along the loop, but those measurements come from absorption lines. With the GBT data, we were hoping to be able to map out to see the structure of each phase independently through some data analysis. So Mukesh has been using a code, ROSA, that I developed during my thesis, and I'm gonna describe this code very briefly to you in a minute. But before that, I would like to just highlight this observation of the central region of the spider at higher resolution, 1 arc-minute. That is a combination of interferometric data from DRAO, plus for the single dish data, the combination with single dish data, the GBT data that you just saw. If we want to have science-ready product to work with, it is critical to be able to combine those interferometric data with single dish data, here the GBT. This quite incredible network of filaments that you see here at the center of the spider is a strong indication that there is a lot of cold H1 gas in the NCPL as well. So going back to ROSA, in a nutshell, I developed this code to be able to map out the different phases of the neutral ISM, to map the warm and the cold phase from an H1 PPV. And we achieved that by developing a new Gaussian decomposition code that takes into account some spatial coherency in the parameter space. You can see an example here where we see the Gaussian decomposition scanning from left to right in an H1 PPV cube, and you can see that the solution is spatially coherent. The Gaussians move together, such as when we sort those Gaussian into two categories, narrow and broad for cold and warm, we can map out in a spatially coherent way the different phases that we have in those H1 PPV cube. So Mukesh used ROSA on this square region around the spider, and he was able to identify 4 different distinct phases. The first one is CNM. We knew there was CNM, so strong component of CNM. This is really what the component that bears the structure we see on the sky in the dust map, for example, the spider, the legs, the arms, and the connection to polars. There is also a little bit of unstable gas. Also, the two maps are there's a bit of degeneration between the two. But the main takeaway here, and this is, we believe, a robust result, is that the combination of the two along the loop dominates the mass in the spider. There is a massive condensation of H1 gas, and that's consistent with what we see with absorption data. There is one component of WNM centered around 0 that we see over the whole sky. It's always there, diffuse components along the line of sight. But very interestingly, we found a 4th component, a very well-defined arch that sort of encompasses what we see in the cold gas, the structure of the loop. And this gas, this warm gas, is moving at a velocity of about 14 kilometers per second. So we can start to link what we see here with what I mentioned at the beginning of this talk, which is this velocity gradient from the north right part of the field to the south eastern part of the field. And this warm arch is about 1/3 of the mass along the arch. So this is really an important component in terms of mass. So if we go back to a more large-scale picture of the NCPL, combining GBT and EBIS data, and no more Gaussian decomposition, we just take a channel map at the velocity plus 14 kilometers per second to see what is happening here. So of course we see this arch that we detected through this Gaussian decomposition. But most surprisingly, we also found, and that was not in the decomposition, not in the squared region around the spider, that on the opposite side of the cavity, there is also a little arch. So we start to converge towards the picture where this moving worm H1 gas encompasses the whole cavity. So to arch, I can overplot them on a just optical depth map from Planck, just for you to see how they fit in the picture of Ursa Major, the spider, and Polaris. But this is really the main takeaway of this paper, of this work, is that we think we're seeing here some sort of relic of the dynamical process that compressed the gas and was at the origin of the formation of this structure of those cold, dense clouds, which are now forming molecules. So for the few remaining minutes, I would like to bring you to my browser and show you some interactive figures to try to show you in 3 dimensions on top of 3D dust map how those 2 arch fits into this picture of a hot cavity, an expanding cavity. So I hope you may be able to see this. The first one I would like to show you is, so this is a dust extinction cube of the second quadrant above the galactic plane. So it takes a little bit of time to orientate yourself, but bear with me, the sun is there, and I'm gonna try to just orientate the cube such as it looks like what we see on the sky. So here we have one arch, the second arch, Ursa Major here, Polaris, and the spider is hidden somewhere there. And all this gas is like galactic plane gas. So I'm going to slowly rotate this cube, such as you can see where are the different clouds. Here again, we have Ursa Major. The spider starts to appear here. It's this thing here, a little bit closer to us than Ursa Major, and Polaris in the background here. So this is showing you the fairly dense gas in the dust extinction cube. And this is quite neat to see that all the dense cloud, Ursa Major, the spider, even though it's closer, they lie on the surface of this cavity, this elongated spheroid that is really reminiscent of this early model of a cylindrical cavity. Now I would like to show you a last figure that is this time not showing you the high dust extinction, the high density gas, but the very low density gas is basically reaching the limit of what we see with this dust extinction cube. But it's still useful to see where there is nothing, because where there is no dust, it's potentially reaching the warm and the hot gas. And then here we see emerging the full picture of this cavity that we think is a protrusion of the local bubble. The local bubble is here, we're inside the sun, and we have this old cavity where there's basically no dust. And around this cavity, we see this moving H1 and a lot of condensation, a lot of CNM forming in clouds around that live on the surface of this cavity. So I have more minutes, and I would like to conclude this presentation. So the main takeaway for this talk is that we see a very important phase transition that has or is occurring in the NCPL. The H1 bears a relic of the compression events, this warm moving gas that encompasses the cavity. And through analyzing the 3D dust map, it shows that those dense clouds are located on the surface of this cavity. This cavity can be modeled with a prolate spheroid, or it's very close to this early model, the cylindrical model for the cavity. So reminiscent from this work by Meyerdierks in 1991. Thank you for your attention.
Thank you very much, Antoine, for a most interesting presentation. Thank you. Let me remind everyone to submit questions through the Q&A button on the lower central right part of your screen. And I'd like to start by asking, again, maybe you could put one of your slides back up. What is the relationship between this structure and the Radcliffe wave?
Oh yeah, this is something I didn't touch on. I can very quickly show you an extra plot here that is looking at the whole solar neighborhood, just not the second quadrant above the plane. And when we have this full picture, we see that basically the protrusion of the local bubble is in the direction of this Radcliffe wave, in the direction of the local harm. So potentially there is something that is related to all the star formation activity occurring along this arm. Maybe the cavity was there formed by star formation, and then warm gas is flowing from the local bubble or from the lower halo into the local bubble.
Mhm. Okay, we have a question. Said, I may have missed your earlier argument, but how did you separate the CNM and WNM based on the H1 data?
Yeah, so it's really from this spatially coherent Gaussian decomposition. We just assume that H1 data can be described with a sum of Gaussians, which we believe is a fair assumption. But it's a superposition of through the thermal broadening of the line. We can try to separate the contribution of the different phase, because one is going to be described by broad Gaussians and the other phase by narrow Gaussians. So it's just a fit of a multi-Gaussian model, but we just do it such as the solution is spatially coherent. It just helps having a better solution, because the decomposition is very degenerated by nature. The model is highly nonlinear.
Okay. Have you looked into molecular gas, for example, CO, towards this region? Is it accumulating around the cavity?
Sort of, because there is a lot of CO in those regions I mentioned, also major polarized. In the spider, there's been detection of CO. GHIGLS in Canada at University of Laval has worked a lot on mapping CO in the spider, but it's harder to detect, I believe. But the spider is really at the top of the loop, so there might be something related to the physical properties changing with galactic latitude or something, so more local condition. There's also this very recent work in Ursa Major by Rafael Tritsis, who's been working with CO data, I believe, and more like studying the magnetic field, the H1 to H2 transition. So definitely a lot of CO.
Mm-hmm. Is there any evidence for the origin of this object, this compressing wave?
So as I mentioned in one of my first slides, there is no OB star, so it's hard to relate that to temporarily directly to some site of star formation. The picture that fits better with this diffuse source of energy is really that which has to have hot gas flowing into maybe a pre-existing cavity, because the interstellar medium is not this smooth homogeneous medium, and the local bubble that was this massive explosion is filling the entire bubble with hot gas, and there are a lot of known tunnels where this gas is flowing. So the NCPL might be one of those tunnels, and through pressure gradient, just expanding the gas and forming this cold medium around. It's still a bit unclear, but that's the picture that we have in mind at the moment, as opposed to a supernova explosion, for example.
Okay. It's another question. In the title of your talk, you mentioned condensation. Could you comment on that?
Yeah, so the condensation that was really referring to the condensation of H1 in this case, the fact that we see a lot of CNM. Now, the tricky part is that when you have H1 observation and you do this multiphase analysis, it's tricky to know in which direction the gas flows. Was it there, and we have WNM because CNM is turning into the warm phase, back into the warm phase, or is it the condensation in the sense that it was warm gas, and through the compression we see the formation of cold gas? that we call a thermal condensation. The condensation is really referring to this thermal condensation, but you need to compress warm gas at some point to have thermal instability develop in the gas and have a thermal condensation. So that really also fits with the picture of an expanding cavity.
So in the diagrams that you showed of the shell, the 14 kilometer a second shell, when you look at it spatially, you have it quite extended along the line of sight.
Yeah, in the 3D picture, yeah, that's maybe a bit confusing. So in the 3D picture, we don't know with H1 where it's located, right? So I was just showing with those blue arches in 3D the possible location of the arch based on the peak we see in the 3D dust extinction profile. But maybe I should change this. It's a bit confusing, and the worm gas could also be like just all along the cavity. It doesn't have to be localized because it's not cold, it's not dense. It doesn't have to follow the dense dust. It can be just a layer of diffuse gas along the cavity.
That would give a quite different pressure than if it were more condensed.
That's true. That's true. Yeah.
Okay. That finishes our open questions. We have any more questions? We have just a couple minutes left. And let's see if there's stop for a second for any more questions. And while we're waiting, let me remind everyone that this webinar has been recorded and will be available for viewing on the greenbankobservatory.org website under the science section, probably certainly by tomorrow. Since there are no more questions, I want to thank Antoine again, getting up so from Canberra to give us the results of his research. 2 weeks from now, we will be crossing the Pacific and the North American continent to Vancouver for the University of British Columbia, where Ingrid Stairs will give us a talk on tests of strong field gravity with the double pulsar. We hope to see you then. Thank you and goodbye.
You.